Great. Very glad to present our solution that has won this competition this year. So thanks to Daniel, who has already told about the competition and new challenges that have been introduced this year, like different tracks. The problem statement is also known. We have like a grid, we have a rotation action model, so we need to take into account the orientation. We have collisions, and we need to take them into account when we are doing planning. We also have task scheduling problems that we need to do some valid plans where we cannot assign same task to multiple agents, that we cannot reassign tasks that has already been opened, like been executed or something like that. And our solution, it actually quite repeating the solution that was made a year ago that were called VPPL. And we also use some fast rule-based solver to find an initial solution within like milliseconds. We also use some large neighborhood search optimizer to efficiently use the provided computational resources, to use all times that we have. And we also have graph guidance technique to reduce congestion between agents, because we don't plan for like full horizon planning, but we plan for just a few steps, and we need to somehow distribute agents along the map to reduce congestion. And for scheduling track, we created some easy but fast and efficient greedy approach that allowed us still to win even combined and scheduling track. One of the key features of our solution is concept of operations. In original PIBT approach, it performs like a single action. So in this case, when we have rotation model performing only a single action, we can reach only two possible cells. On the picture, they are shown in red. This is bad for us because we cannot eliminate collisions performing only like a single action. We cannot free a cell. We need still to rotate before we need to rotate, and only then we can like move somewhere else. And the presence of rotation actions, it actually reduces the amount of cell sequences. So we don't need to consider 4 power length possible cell sequences. Instead, we can discard most of them because many actions result into the same positions during time. So it doesn't matter whether we will first rotate or wait, or we first wait and then rotate, because from the perspective of collisions, it's the same, and agents occupy the same cells. And we have considered operations of different lengths, starting from 3 to 5. And as you can see, even operations of length 5, we have only 136 unique cell sequences instead of like more than 1,000 if we have a non-rotational model. Here we can see the pseudocode of the proposed approach that we called simply enhanced PIBT. And it actually mostly repeats the original approach with some key differences. First of them is operations. Like I've said, we have like operations that consist of multiple actions. And as we have many of them, not only 5, many of them may result into the same distance to goal, which is used for prioritizing them, for sorting them. And we have added some additional breaking ties coefficient that prefers moving actions over rotation and rotation actions over waiting. So we force agents to move somewhere if they can. Second difference is that when we have multiple forward actions, when we occupy multiple cells, we may collide with more than one agent. And it's actually hard to run this recursive PIBT procedure. It might be time consuming, and we just skip the operations that have collisions with more than one agent. And last thing that might be counterintuitive, that we actually use priorities of the agents only for their like initial ordering. And we allow agents to have collisions with any agent, even the ones that have higher priorities. And to optimize the solution that is found by PIBT, we use large neighborhood search, and it works as follows. We select just some agent randomly and remove its path and run PIBT procedure for this agent, but to add some exploration, to change the solution, to find something new, we skip some of the operations with some probability. In our case, it was 30%. And we also used simulated annealing to also add some exploration. So there is a chance that we will accept a solution that reduces the metric. However, we are trying to maximize the reduction in distance to goal with respect to priorities of the agents. So here we also use like distance to goal for agents to find out which of them like has high priority. And as we have multi-core processor and we may run LNS in different threads, we run it multiple times and just choose best found solution out of them. So there were no synchronization between threads. We were not trying to like reuse some other best found like solution or something like that. And in our case, it occasionally works best than some other techniques where we were trying to use this like synchronization mechanism or something like that. We also used graph guidance technique, and we were actually not using any existing approaches described in the papers like traffic flow or something like that. We also didn't use any dynamic update. So our graph guidance is static. It's made initially, and using it just compute distance table, and we further use only distance table. We have made a handcrafted graph guidance for a random map, as it's quite small and half of the instances were actually evaluated on this map. And for other maps, we have made a simple rule-based graph guidance. Some examples you can see here on the slide. So, and penalty for actions that are not preferable, they have 10 times higher cost. Talking about scheduler, we made the following approach. I will just show you some example. So preliminary, before we start to distribute tasks between agents, we compute some costs like distances between errands, distances between agents and tasks, and sort this task based on like this full cost that takes into account both distance to task and the cost of the task. And we create a heap picking most preferable task for each agent. In this case, you can see that all agents prefers task T1, so heap contains all pairs with T1. And when starts main loop, we pick out of this heap the best pair. Like agent A1 wants to pick task T1, and it has the best cost. On the next step, if task is already picked, we cannot pick this task for other agent. And we push into heap next preferable task. For agent A3, it's task T4. And we continue this process until all agents have their tasks. So on step 3, agent A2 tries to pick T1, which is unavailable. On next step, agent A3 picks T4. On the final step, agent A2 picks task T2, and we are done. So it's quite easy, it's very fast, and it's worked quite well. Additionally to the results of competition results, we also made some experimental evaluation of our approach and wanted to evaluate how each of our piece of our solution influences the results, like graph widths, adding of large neighborhood search, etc. And we also made a comparison with the winner of last year competition. And as you can see, our solver is able to beat it. And our decision time, it actually substantially higher than the runtime of classical PIBT algorithm, but it provides much better results, much better throughput. Here is the results, some demonstration of weighting heat maps. So you can see where agent perform weight action during the episode, and as expected, graph widths, it allows agents to distribute agents more evenly over the map, and it reduces the overall congestion and number of waiting actions. Another example on another map, game map, and as you can see, we have some narrow corridor where many agents tries to move in both sides, and in this map we actually made the same trick where we were disabling part of the agents to raise the overall throughput. As you can see, the highest throughput were achieved at around 3,000 agents. These are the results on the tests that were made on the competition instances. And the first column, it shows our best achieved results. And as you can see, in the end, we have some a bit lower results because we have disabled some tricks, some optimizations that were made for specific instances. And even in this case, we are able to achieve 9.5 score. And the major key feature, as I have said, is our enhanced PIBT version that actually work best on a small random map with a high amount of agents. And here is example with 800 agents where we have almost 100 density. And even in this case, we are able to produce some good results and significantly outperform all other competitors, including second best team, Kitty That's our conclusion. It's allowed us to win this competition, but I also want to point some thought, which may be further discussed during the discussion session, is that developing a solver for competition it's actually not the same as doing research, because we are focused on particular set of instances, and we need to create some specific optimizations or even some tricks to get a high score. And you have less control. You cannot modify the problem statement. You have a fixed problem, and you need to adapt to it, even if your solver needs something else. And beating existing state-of-the-art approaches doesn't guarantee that you will win the competition, because you have other competitors and they might create something new, something better. And as you can see, our solution, it doesn't have any complex ideas. They all are quite simple, and yet their efficient implementation allowed us to win this competition. And of course, there is still a big room for improvement, both in terms of the approach and the implementation. And this work is actually on progress. If you wish to see it, there is a link to our GitHub where you can see all the progress. Thanks for your attention.
Thanks, Anton, for the presentation. So now is question. Due to the time limit, we might not take lots of questions. So feel free to unmute yourself if you have questions.
I have a question. Can you hear me?
Yeah.
Yes.
So what is your graph guidance look like for a map like warehouse?
I actually showed it. It was like simple rule based. So even rows have higher cost for moves up, and uneven rows have higher cost for move down, and same for like left and right actions. So it was quite simple.
I mean, the intersection is going to have like two preferable move.
I didn't get the question.
There's an intersection between the even row and the even column.
So maybe it's better to show you again. So green columns means that we prefer to move up, and yellow columns show that we prefer to move down. And same for left and right. So we have like this graph guidance for actually for like each action for each orientation.
Okay, thanks.